With recent evolutions in composite material technologies, aircraft composition has started to change. The commercial aircraft industry now incorporates an increasing amount of composite materials in their structures. Composite components have the advantage of being light and robust. The composite structures are typically shaped in complex and variable geometries, and this creates a challenge for NDT inspection. The preferred NDT method is phased array UT. Standard phased array UT inspection requires a precise alignment between the probe and the specimen. In the case of complex geometries, this typically involves complex and therefore expensive mechanical systems and an exact knowledge of the specimen geometry. Recently, Zetec has implemented the time reversal technique. This is a real-time adaptive process, allowing for rapid and reliable phased array UT inspections on such complex geometries. This video will illustrate how state-of-the-art phased array units controlled by UltraVision software can be used to apply the time reversal technique to improve coverage and detection capability of ultrasonic beams for various CFRP geometries. The structures to inspect include the fuselage and different parts of the wings, the skin, stringers, and spars. All these components have different shapes, mostly quite complex, so the examination method must be able to adapt to those challenging conditions. The manufacturing process of composite materials can generate different types of defects, porosities, foreign bodies, and delaminations. Zetec offers an efficient solution for composite material inspection. This solution is driven by advanced PAUT hardware, quartz, zircon, or topaz 32. All the units can be controlled from the UltraVision software package. Multiple acquisition units can be controlled from a single software interface. The Zetec solution is flexible and can be integrated to the customer's pre-existing manipulator. To optimize the detection capability, the probes must be carefully selected according to the specimen geometry. The inspections are performed essentially at a normal incidence with the component surface. For the typical composite shapes, this typically requires a combination of two types of probes. A linear 1D phased array probe is used to inspect flat surfaces. These probes typically have 32, 64, or 128 elements. For curved sections, arc-shaped 1D probes are used, with typically 32 or 64 elements. Time reversal is a real-time adaptive UT inspection technique meant to eliminate the effects of misalignment between the probe and the specimen. This is achieved by using surface profiling. This process uses the time of flight from individual elements of the probe to characterize the surface of the inspected specimen. Once the surface profiling is complete, compensation delay is applied to the individual elements of the probe, and essentially normal incidence of the beam on the surface is achieved. Now this is a two-step process. The first step is surface profiling. During this step, a plane wave is generated by firing all elements simultaneously. When the wave meets the specimen, it is reflected back to the probe where it is received. The reflected wave is no longer a plane wave. It is affected by the shape of the inspected component. The variation in the wave shape translates into a different time of flight for the response on each individual element. Using the different time of flights measured in the initial firing, the software calculates the delay for every individual element required to compensate the differences introduced by the surface profile. This process can be repeated several times until the wave reflected from the surface back to the probe is a plane wave. The second step is to record data using the delays obtained during the profiling phase. Data acquisition is performed using electronic linear scanning with a limited active aperture. The complete process is performed real-time at each scan position and can maintain a scanning speed similar to standard phased array UT when using equivalent UT settings. Throughout the next data imaging sequences, the left side data sets represent a traditional phased array channel, while data on the right side shows the time reversal technique. In this first example, a 1D linear array probe at 5 MHz is used to demonstrate the angular misalignment tolerance of the time reversal compared to traditional phased array. The 5 MHz probe has 64 elements, a pitch of 0.6 millimeters, and an aperture of 6 elements is used. Both channels have the same gate synchronization settings and the same amplitude threshold. When this threshold is not reached, the signal is not displayed. The video feed from the probe shows that the traditional phased array channel loses synchronization even at slight misalignment. The time reversal channel stays synchronized and maintains a stable amplitude even at large misalignment. This illustrates the capability of the time reversal technique to provide high-quality inspection data for varying geometries. To demonstrate the inspection capability of the time reversal technique, a case study on a representative specimen was performed. A CFRP sample was manufactured for this purpose by an industrial composite provider. It has typical composite material attenuation and contains multiple artificial brass inserts to simulate typical defects. During this data acquisition, the scanning was performed with an intentional misalignment angle to show the difference in imaging quality. The colored C-scan images demonstrate how well the time reversal channel performs, while the traditional phased array channel displays additional noise, thus making defect indications harder to identify and characterize. For the curved section of the specimen, the same 1D linear array probe is used to demonstrate the better coverage when using time reversal. The traditional phased array channel covers approximately 10 millimeters of the specimen. At the same position, time reversal channel has a coverage of around 30 millimeters. This extended coverage facilitates the detection of additional flaws. Another benefit of the time reversal technique is the ability to easily determine the fiber orientation within CFRP material. Time reversal stabilizes backwall amplitude and straightens the interface echo, making it possible to examine large areas of a curved component. The bends often contain fiber weaving that can be noteworthy for the specimen integrity. In the case of our sample specimen, fiber weaving is also called tiger stripes and can clearly be discerned in the time reversal channel when using soft gain on the Gate 2 amplitude C-scan. With time reversal, Z-Tech offers a powerful technique that is able to compensate for mechanical probe misalignment and misorientation in real time without sacrificing scanning speed. Time reversal enhances flaw detection capability and improves porosity assessment by stabilizing the back wall echo amplitude. By mitigating the need for exact alignment and orientation, time reversal can drastically reduce the cost of mechanical scanning systems. The time reversal technique is available as an option with Z-Tech's Zircon, Quartz, and Topaz 32 units. By connecting multiple units together, multiple probes can be fired in parallel, thus offering the potential for a substantial increase of the scanning speed. More information about our products is available on our website, www.ztech.com. If you have specific questions, or if you want to find out how this Z-Tech solution can help you make your inspections more reliable and cost-effective, please contact us via info@ztech.com.